Thank you very much, and welcome to my talk, my first and last Shellcode loader. I currently work at Raiffeisen Switzerland, the now second largest bank in Switzerland, as Red Team lead. I also made a presentation last year at HITB in the box in Phuket. So my talk is divided in a few sections. I will start with a little introduction. Then I will discuss the antivirus techniques. Then we go over to EDR basics and some anti-EDR techniques. Then to my actual tool. And then we discuss basically both together. Most likely it will take a little bit more than 1 hour. Let's see if I can do it. So the target audience are RedTeamers, which are a little bit confused about the EDR. RedTeamers usually do initial access. Who is Red Team here? And who wants to do red teaming? Usually everyone. So usually at the part of a red teamer is we take some C2 framework like Cobalt Strike, we somehow send it to a victim, and then the hacking begins more or less. Usually you will encounter something like this. The export functionality of a C2, which can generate executables, which nobody uses, and today you will see a little bit why, and most of the time we'll just use some shellcode. To gain initial access, we'll need to send this beacon or implant to the user. There are many different possibilities nowadays. Geeky discusses a lot of it, but today I will talk about PE. Files, so top left here. First, to give a little bit of feedback and fundamentals, I will talk shortly, 5 minutes about processes. I hope for some it's maybe new information. We have usually a program, an executable file, which has code section and data section. This is a program. It's stored on the hard disk. If you double-click it, execute it, it will be transformed into a process in memory, in RAM, by the Windows loader. Usually, there's different detection capabilities for both of these things. So the typical antivirus is file-based, also signatures, or static analysis generally. On the other side, we have processes, the running program, then you do dynamic analysis or behavior analysis, like memory scanning, sandbox, debugging, also the EDR. These memory regions have similar permissions like Linux files. Usually they have read permissions and they can be executable or writable. Nowadays, because of exploit protection, you don't want to have a memory region which is executable and writable at the same time. So the code is executable but not writable. The data section is writable but not executable. There's also a difference between backed memory regions and unbacked memory regions. So memory regions which are coming from the PE file get copied directly into the memory. They have a backend, a backed file or a file backing it. And if you virtual unlock some memory by yourself, then it's unbacked. You can use a tool like PE-bear, like here. You see all the sections on top. Text section is the code, R data, and the other data sections are then the data used for the program. On the left side, it's the file layout. On the right side, it's the memory layout. If you use a debugger like x64 debug, you'll see all the dozens or maybe hundreds of memory sections in memory. Here it's the executable with the text section highlighted, which is executable and readable, and it's from an image, which means it's backed. For some people who don't know what a shellcode loader is, first you need a shellcode. in this case, as an example, a shellcode which executes calculator, Windows calculator. When you do a hex dump, it doesn't make so much sense, but of course, if you disassemble it, it's just plain assembly code, your shellcode, which is a little bit specially formed, but you can just put your instruction pointer register in the CPU on this memory address, and it will start executing your shellcode. Usually you take the shellcode and copy it somehow in a source code file, like in this case, and then do an allocation for a memory region, for example, with full permissions, read, write, and executable, copy the shellcode there, and then execute. So there's usually always the same procedure. You do a virtual alloc, get a new memory region, then you copy the payload into this memory region, and then you execute this memory region, which now contains your shellcode. Each of these steps can be performed a little bit differently. You can execute it in different ways, for example, with create thread or just jump to it. There are different possibilities to copy, but overall it's always these few steps. You can also do it in other languages. This is an example of our internal SOC, where they downloaded the shellcode from the internet, basically from a remote host, and they've written the loader in C#. It's also allocating memory, copy the shellcode, and then execute it. You can also do it in PowerShell. Shellcode in a variable, then alloc h global, copy, then get like a function pointer and execute it. You can even do it in Visual Basic for application in Word. So you can import anti-DLL or kernel-32 and do the same stuff. You can also do it in other processes. So Windows provides the open process call API. So you open a remote process when you have permissions, allocate the memory there, copy the shellcode, create a new thread, and then you have your shellcode running in another process. These are the basics. Now we go to the antivirus, how this one works. And basically, we need to have the payload somewhere. And if you just do with no encryption, default, the payload, our Cobalt Strike or Metasploit or whatever, will be plain text in the file itself, in the executable file. When the system writes this file to disk, the antivirus will get the write file event. It will scan the file for signatures, for known bad, and then if it detects something, remove the file. So we can show this. Like here, I will show more details about this tool later. I will include the Metasploit shellcode into a loader, basically. So we have the metoperator here. And I have no encryption. I whitelisted this directory where I create the executables. So this is not being detected. I copy it in my downloads folder. And after a few seconds, if everything works, Defender should come and complain that there is, yes, a malicious file here. So it detected Metasploit hack tool. Good. So that's what is expected. Now, the obvious solution, of course, is to encrypt the payload. So we don't want to store it in plain text. We want to encrypt it so the antivirus will not find it. In my opinion, the encryption can be anything. Can just XOR it or base64 it. Doesn't matter. There's no need to get some advanced AES encryption or steganography stuff or whatever. So let's do this too. I will change the encryption to this. And rebuild my file again with the Metasploit, but this time with a XOR encryption with a random key. That's number 2. If you copy it in downloads, Defender should not detect it anymore because it is encrypted, but it's detecting it. I have to give it some time, probably. So usually there are pop-ups, but when you're like in presenter mode, Defender doesn't like to show the pop-ups. Yeah, so he removed it. We see it here on the right. And he has detected my infected2 file as a metapredator. If you do a loader, a shellcode loader, you will see this problem, and people are confused, like, I encrypted my payload in the file. How is it possible that Defender detects my encrypted payload? Do I need to add more encryption? Does it upload it into a sandbox or whatever? What is the reason? And then they have weird solutions like encrypt it more or download the shellcode from the internet, but actually it is pretty simple. Antivirus, since like 30 years, have an emulator inside. So that it will, after scanning for signatures, it will open the file and start interpreting it on its emulator. So that's not virtualization, it's not a sandbox, it's not full emulation like Box, it's not like half emulation like Wine. It's more an opportunistic, minimal interpreter of x86. Here's a symbolic picture. It doesn't look like this, but you can imagine you just go through the opcodes and re-implement the functionality. This antivirus emulator will open the file and start emulating a little bit, and usually it has a cutoff time. So this cutoff condition, this cutoff condition can be some time, maybe 10 or 100 milliseconds. It can be number of instructions, number of API calls, or even the amount of memory used. Okay. So the antivirus emulation will emulate until if you're not breaking it, so we can basically add anti-emulation functionality, build it again, and then the idea is that the file will not be detected anymore. So that's number 3. Copy it again in downloads, and this will be not identified by Windows Defender anymore. The content is still encrypted, like with number 2, but we have now some anti-emulation implemented, so the emulator will not find our decoded payload. So the problem is, if it's emulating, it will scan the memory after the condition is met, and if the metapredator is in memory, it will find it with the signatures, and the anti-emulation function will stop this. The code, which is still responsible to load the payload, is still in the binary, of course, and can be identified by static code analysis, but it's not being executed anymore. So this I've shown. There's a closely related problem in the days of red teaming, and that's Middleboxes. What I mean with Middleboxes is basically antivirus not on the end system we try to compromise, but on the boxes in between. Like if you send an email with a malicious attachment, the email gateway will scan it, possibly execute it in a sandbox, in a virtualized environment. So more powerful than an emulator. It doesn't matter so much if an email arrives 1 minute later or half a minute. There's some time to do some more analysis. But what is usually being done against this is the technique called execution guardrails. You just do an environment check. As a red teamer, you should anyway do this, that your malware is only executed on your customer, not somewhere else. So you can basically just check if the host you're executing the malware on is in the right domain, like the domain of your company. There's also the environmental keying, where you take some information from the system, you know it's there, and then take this as a key to decrypt the payload. I don't think that's so useful, but it hinders reverse engineering. If you copy the executable away, you don't have necessarily the information anymore. The same thing, just opposite, is sandbox or virtual machine detection. You can just check if you are in a sandbox, for example, by the number of CPUs in the system, VMware, strings in the drivers or whatever. So that's more used by threat actors who don't have a specific target, but just broadly distribute the executable. So this is very similar to the anti-emulation. The sandbox will get the executable, it will start it. We have the execution guardrails which will say, no, this is not the right system. I will not decrypt my payload, so it's not malicious. So if you combine these two things, we have the execution guardrails, which are usually put at the beginning, and then the anti-emulation, which I think it's very unknown for some reason. Even I forgot that this anti-emulation exists in antivirus software, and you need to handle this. And I see so many blog posts which then have the title EDR bypass or whatever, because they do some triple encryption, which just by chance defeats the emulation of the antivirus. So this is good against the antivirus emulator or for Middleboxes. Now we are on our target, basically the user we want to compromise. And there is usually an EDR is installed, and we need to bypass the EDR. The execution guardrails will see it's on the right target. It will not exit. The anti-emulation will just be performed when the user double-clicks our executable, and nothing happens, and then the payload will be decrypted and the EDR sees it. So I will show a little bit the basics of EDRs as I see it. EDR is just an agent on each system, and it finds malicious processes. So it's like here Dr. Dre, who tries to identify the real Slim Shady, and cannot just tell him to stand up. Nowadays, still EDR is a black box. We don't really know how it's working, but what we know, or what we can find out, is the input to the EDR. What events does it handle or can handle? And in my loader development, I created these bubbles of pain, like the pyramid of pain, but a little bit different. So usually you start with the file scan, the antivirus. This to defeat this, it's very easy. But then you go down to the EDR part, which observes behavior and telemetry of the system. And if you defeat this, you also need to defeat memory scanning. I will talk about all this later. And if you want to defeat all three, you basically just turn in circles. I didn't find a complete solution, except maybe a complete obfuscation of the tool. So one of the most famous EDR inputs are user mode hooks, which some also call AMSI. So a process on x86 usually, or doesn't have access to anything. It can just access memory, RAM, and the CPU. A process cannot access files, it cannot access network, it cannot access other processes. It has no idea or concept of these things. It needs to ask the operating system to do this kind of things. The API basically to the operating system in Linux are system calls. On Windows, it's anti-DLL. So if you want to ask the operating system to do anything, you usually issue a system call, but the API in Windows is defined by Microsoft as anti-DLL. So it's a DLL which is loaded into each process, and this DLL will issue the system call for you. Usually the normal code will then call other DLLs, like here open process and kernel-32 DLL, but it always ends at the anti-DLL. Anti-DLL will issue the system call. So people got the idea to hook anti-DLL, to intercept all function calls to the operating system and log it. So basically it's a patch of anti-DLL. You just add an instruction, here to jump to your callback. So antivirus or EDR vendors inject the DLL on each process, patch anti-DLL to point to this DLL, and this MC-DLL will then forward all events to the EDR here at the bottom. Usually not all Windows API functions are hooked in this way. There's usually a smaller part of it. So if there's new development of weird API calls for an API, then maybe the EDR doesn't have visibility. I found this overview. Sorry, I forgot from where. But anyway, you can see that hooks in anti-DLL, not every EDR is doing this. Most notably, Defender doesn't seem to do this anti-DLL hooking. But there's more. It's not the only thing an EDR can consume as an input. It was one of the first things and one of the only things most people think of when they talk about anti-EDR, but actually the EDR also consumes kernel callbacks, ETW and ETW TI. And I will talk very quickly about these three things. So the kernel callbacks are basically these four callbacks: create process, create thread, load image, and the more generic OB callback. You can see that's the function definition in your kernel driver. And you get like the process ID which created a process or a thread, and the thread ID and a little bit more information, but not really a lot. If you want to see this for yourself, you can use Process Monitor, disable 4 of the 5 icons here, so it just have process information, and that's basically the same thing. You see thread exits here, load image, process create, and information from the system to this. Then we have ETW. ETW is event tracing for Windows. That's like a high performance tracing infrastructure. So it's not logging like syslog. It's more like dtrace. There's just two important things you need to know. There are ETW providers and ETW consumers. The EDR, of course, is an ETW consumer. And there are a lot of ETW providers. There's just like several hundred, I think, and each of them provides a lot of different information. In my research, I identified the most important ones always in my talk for loader identification is kernel process and security auditing ETW providers, which again provide the process start-stop, thread and image loads, again process start and stop in security auditing, and some security operations. So again, not much information for our EDR. Kernel process looks like this. That's what I already said. You can basically gain the same information like from the kernel callbacks. Here is security auditing. It has a little bit more security relevant stuff like account logon or I think some registry access, but also process start and stop here at the bottom. Important to know, that seemed to be also a source of confusion. Many people talk about ETW bypass or whatever. So there is the ETW events created by a process, by event write function call. This you can influence as an attacker. The whole ETW infrastructure in Windows usually is out of reach, except you have more permissions. There's also ETW threat intelligence, what I call the good shit, basically. This is from Microsoft itself and has more important security relevant and especially loader relevant information. You can see also the top one is Q user APC to, for example, identify APC injection. The problem is that this ETW TI, it's called threat intelligence. It has nothing to do with threat intelligence. It's just some nice information to have. You need to be a PPL process and I think to have a special signature. So not many EDRs can even consume this data. And for us attackers, you need to basically have a driver exploit to access it. But there's a little bit more. As the events have little information, the EDR needs to provide or access some more information. That's identified like 4 things. That's process information, the call stack, memory scan, and a file scan. Of course, with the process ID, you can access the source image of the file, of the process, and then scan the file again or compare its content with the memory thing. The other 3, I think, have slides. Yeah. So you will never have, for example, the command line, but the EDR would like to provide the command line or the full path of the process to the user, to the analyst. And for this, you need to ask the process, what's your command line? Because it is stored in the PEP. Also in the PEP is the process parent ID, and so it's pretty easy to do this parent spoofing or the command line spoofing. Some information are also in eProcess, so the PEP is in our own address space. We can just modify it as we want. eProcess is in kernel, can still be more or less modified through some tricks, but that's not interesting for today. There's also memory scanning. That's basically identical to file scanning. You just scan the memory, usually the code section and the data section, for malicious signatures like Metasploit. One important and more or less new thing, but very powerful, is call stack analysis, or just the call stack. The EDR is able to access the stack of a process, of course, and then can walk the stack and find the parent functions which led to this function call. In this case here, the call stack looks pretty nice from 0 to 7. It's like text and whatever, and at the bottom there's just some weird text numbers. That would be pretty suspicious for an EDR. There should be a clean call stack till the end. So the EDR, this can be, for example, also be done in MC, as you anyway hook the function call invocation. You can just walk the stack and give this information of the call stack also to the EDR. Elastic is doing a lot of things. It can identify direct syscalls, callback-based evasion, module stomping, and more. And if you think about it, and it's clear that this is all possible. One of the most important things is the performance of the EDR. If the EDR is slow, people will change to Mac. And that's not good. Microsoft cannot let this happen. I've seen that Microsoft introduced the dev drive protection. In our company, we also have a little bit this issue that Defender slows down certain systems. For example, developers who use NPM or other build pipelines which create a lot of files every time you compile it. So I think there's a different performance impact of stuff the EDR can do. Just correlate an event is pretty cheap. If a process opens LSAS, that can be immediately an alert. If you need to correlate several events, it's a bit more expensive. If you have to query the process for information, it will take even more time. And if you want to do a memory scan, that's maybe you need to access megabytes of memory. That's even more expensive. And file scan, of course, then you're pretty much lost. It should have been done before. Usually, or many attacks on EDR, surprisingly, are based on time. So there's a time between the EDR receiving an event and then acting on it, like gaining more information. One example would be memory encryption. You just do your thing as a beacon, and then you go to sleep, and when the EDR accesses you, then you're already encrypted and nothing malicious is going on. So this is an innocent slide, but it's powerful to think about this in the EDR. Some people heard about Sysmon. Sysmon is basically just a tool which consumes some ETW events, adds some information, and then spits it out again with this additional information. Good, I think I'm well in time. So I will now show some example attacks which have been discussed in the last few years, some EDR attacks. And one of the most famous, and everybody is doing, is the user mode hook patch, or generally probably said an EDR bypass. So as the EDR has the anti-DLL hooked, we can just remove the hooks. So we do some fancy things. We make the anti-DLL code section writable, for example. We store the anti-DLL from disk with a clean version, make it executable again, and then we don't have the EDR is then blind. EDR, of course, can try to identify this mechanism. I think that's pretty straightforward, but EDRs don't seem to be so reliable doing it. And to do this, often people use direct or indirect system calls. Direct system call is just to issue the system call by yourself, not using anti-DLL. This usually requires you to extract the system call numbers from anti-DLL or have it some other ways, and then just issue the system call from your text section. This will leave the call stack, when you do this, will look very, very obviously malicious. So people started doing indirect system calls. Then you don't issue the system call itself, but you jump to the instruction in anti-DLL, which issues the system call. Or in other words, you just jump over the callback in anti-DLL. So in both cases, this user space hooking will not show any information about what you are doing. So the EDR is basically blind if it only depends on this user mode hooks, which not many EDRs are doing. Next is call stack spoofing. As I shown before, this looks very suspicious with the bottom, but it's pretty easy just to clean it up. It's in our process space, it's our stack, we can do with it whatever we want. So here it's the thread stack spoofer.exe, which is cleaning up the stack, basically. So we have control over our stack, and even this call stack spoofing can be implemented basically stealthily without the EDR knowing, and effectively. There's also another technique called image spoofing. You can just start a genuine process like Notepad, then carve out the content, remove the Notepad code and overwrite your own beacon code, write your own beacon code into this process and then resume the process. So it looks more non-malicious. A very similar technique is module stomping, which is identical, but you use DLLs. You basically force a process to load a DLL, in this case OpenSSL. Then you remove all the content of the OpenSSL DLL in the text section, copy your own stuff in it, and then start the thread in this DLL, which now contains your own code. Currently super trendy and a lot of research is being done with memory encryption, but for me it's just one slide. As most of the techniques, we have basically the beacon in memory, like Cobalt Strike. It needs to be unencrypted in memory because it needs to be executed. If it's not in plain text, if it's encrypted, it cannot be executed. And then if it's in memory, without encryption, it can be identified by memory scanning. So the solution for this is every time you invocate sleep, you encrypt your text section and your data section and all your other artifacts. Usually beacon sleep for 1 second, 60 seconds, then check in for new information, and the EDR will usually just see the encrypted stuff in memory. So if you have a little overview, weirdly or interestingly, most of these techniques are based on modifying backed executable memory regions like the text sections, but it seems the EDR doesn't care so much about this. I never had much trouble. Yes. So, perfect. Yeah. Let's go to my tool, the SuperMega loader and the Cordyceps technique, now that we have the basics how EDR work. So my idea is to use the loader, which for me consists of the carrier and the payload itself. We mash it together. Payload, like Metasploit, is encrypted, of course. We have the loader as shellcode, and then we inject it into an existing program like PuTTY or 7-zip or whatever. The start of this idea is basically because I performed some research on code similarity scanning. This is a more or less new technique where you have a large amount of malware, disassemble it, and then find unique things, and then you can find the same things in new files. So this is useful to answer like, are QBot and Picabot related? Because if it's using the same code, then it's probably more or less related. And you can also find new versions of like Crockbot. If they change some parts, move some parts around, the code similarity scanning will still identify the new versions, which I think is pretty cool. What I don't think is so cool is machine learning. Some people attempt to just get a bunch of files, disassemble them too, put them in a neural network, and then it identifies malware. Accidentally, right now, we have a talk, I think, in the main track about this kind of things. I'm not a big fan because I don't think that malware really has much similarities. Maybe in certain areas or families, but if you think about it, what's the similarity between Mimicots and PSExec and Rubeus and Cobalt Strike? There's not so much similarity for a neural network to identify. But people tried, and they try a lot. For both of these reasons, I was thinking about injecting my shellcode into an existing executable. That's like an umbrella. We already have a lot of good code, so we don't need to do good code stuffing. We have meta information, like the company issue. We have the import table already. And it's just nice. I mean, what's the alternatives? Use the executable generated by the C2, or write your own loader, which is then 5 kilobytes big and just consists of malicious code. So I think this is a good idea. And there are 3 ways where you can inject shellcode into an executable. The first one is just overwriting the main function. Take shellcode, copy that main, and it's done. The second one is to copy the shellcode somewhere in the text section and then rewire the entry point in the header of the PE file to point to the loader, which is also not so sexy. And the solution I like the most is to inject the shellcode somewhere in the text section and then patch the main function so it will jump to the loader. Then the loader is not directly into the open. That's not so much my idea. This is the idea from mgeeky, or he did an implementation of this called RedBackdoor, which supports all these injection possibilities. And this was basically the base for my tool. So the main function will look like the left side. The first jump will jump to my loader, which is somewhere in the text section. But of course, it doesn't need to be the first jump. Can be the second, can be the 10th, can be deep inside the code section somewhere. And if you have a security tool which analyzes the executable, it doesn't know where my loader is, basically. Another piece of the puzzle was this tutorial from Hasherizadeh, from C project to assembly to shellcode. And I want to say it's not so much through assembly, but assembly text. The basic idea is that you write C code for your loader here on the left, and then you compile it into assembly text, how I call it, on the right. And this is not disassembly, this is part of the compilation procedure. So we can still modify this assembly text here on the right, which I will also do. So we have basically C templates in my loader where I write the loader and the loader components. I then render them with Ginger 2. I then compile it with cl.exe into assembly text. Then I will clean up this assembly text. She also made a nice tool for this called masm_shc. So Microsoft Assembler make to shellcode. Then the assembly code is cleaned up. Then I can compile the assembly code into an executable and just extract my loader from the code section in the executable, and it will be magically shellcode. Okay, I'm a little bit confused. So basically you can see this here. This is the template of my loader. It's just doing a virtual alloc and it has still some Ginger templating. We then render it and it will include all the things I selected, like the anti-emulation or also the shellcode size here and also the XOR decryptor. Then it will be compiled into assembly. So here is basically the reference to my payload. Then we clean up the assembly. This I will show later. I now modify the assembly and then we compile this, what you see here, and then we have the shellcode. So I wanted to do this, but the tutorial and some other things was a bit obvious that it's malware. I wanted to remove some indicators, basically. And this is what I then call the Cordyceps technique. In every shellcode on Windows, you need to do a PEP walk. So you need to parse the PEP and find anti-DLL, parse anti-DLL, find the function you want to call, like showing a message box, and then you can call this API function. In Linux, it's again different. You just issue the system call, which is way easier and doesn't require a PEP walk. So this will be looking like this. We have the get module in our loader and get function name, and this will call even more code, which in my opinion could be signatured pretty easily. So I wanted to have it gone. And I was thinking, like a normal program, it can just call the message box API. Why can't I do it from the shellcode too? What's stopping me? And I realized nothing is stopping me. So if you have the disassembly of a call to the message box API, it's basically going through the import address table in the PE file. All jumps need to have an address, a destination address, and the import table provides this address. This import table then does some magic to find the real message box in the correct DLL, but this is of no interest. We just want to call the import table. Can you again use PE bear and see all the DLLs which the PE file will be loading, and then user 32 will see the message box API is imported into the executable from the DLL, and it can be called via memory address 2080. And we can just make such a call instruction by ourselves. So if we know at which memory location we are and at which memory location we want to jump, then we can calculate the offset and create this call instruction. So this call instruction is FF15, and then the offset in little endian, that's 1063. You need to subtract 6 bytes. That's the length of the call instruction, because, of course, the instruction pointer always points to the next instruction to be executed, which points after this call. So you have to remove again 6 bytes from the call instruction. The problem it was or is that if you modify the assembly, MASM doesn't have support to do this relative jump. And anyway, I don't know where in the executable my code is. So as it looks at the end, I just write plain C code for my loader. Here, get environment variable W. I don't care. And then I analyze the assembly text, and the MASM will, or the CL, the compiler, will generate these 2 lines. It will basically create the function which will call get environment variable, and it will define an external symbol. So in the future of the compilation process, this symbol will be defined and the call can be resolved and done. Of course, I don't want this. I remove the external symbol from the assembly and just replace the call instruction with some random bytes, a placeholder. Then, when this can be compiled into a shellcode, it will be a non-working shellcode, then it can be injected into an executable like 7-zip, and then it can load it or replace this call with a jump to the import table. So it needs a bit support of the loader, basically, to do this thing, and you need to have a fix-up after the shellcode is injected. And of course, all you need is again to find the virtual address of the placeholder. So you need to disassemble the injected executable again, find the right virtual offset, find the virtual offset of the import table, and then use the function here at the bottom to create the call instruction with keystone and capstone. So I replaced it with a placeholder, and then in the binary again, I replaced this placeholder with the right call instruction, and it looks like it's written in the binary itself, like normal function call. Yes. The same can be done for data. So if we have a normal function call, not in a loader, but just completely normal, you have the data in the data section, that's why it's there. But in a shellcode, you don't have a data section, you have just your code. So to insert data, which you need to use in your shellcode to call stuff, you need to somehow encode it in instructions too. One possibility is to use this little compiler trick on top, where you just put every byte in single quotes, and the compiler will then generate the bottom assembly code, push all the data on the stack, and then you can reference it on the stack. Another possibility to insert data in your shellcode is basically to interleave it. So here you have the string hello world, and you jump over it. Which both solutions, this where you interleave it and this ugly byte pushing into the stack, I also assumed this is very signaturable, so I wanted it gone. So I just do it like a normal program. I inject the data my shellcode is using into the R data section and fix up the shellcode in the binary so it references the data how it should. So then when we debug it, we see here load effective address from this data section, and that's the real data section and my data. This is being used as a execution guardrail. I call this Cordyceps technique. Probably some of you have seen The Last of Us. It's a little bit related. Cordyceps is some kind of fungi which infects animals. It will destroy the brain, but still steer the animal into the open, so the animal can be eaten, and that's more or less, I think, how it reproduces. And my technique is similar. I inject the shellcode into a file, it will break, but it will still look very similar, and I will push it to a user so he can execute it. But from a perspective of an analysis from outside, it will look pretty normal. So I think that's the point where I execute it. Now, currently I didn't click it. It's just on disk. Antivirus didn't remove it. That's already good. Let's start our Metasploit. And if I double click it, I think it's so advanced that it's not being detected anymore. So we have the session, and I think the defender will not detect anything. Yes, but of course that's defender, private defender, basically not really an EDR. So let's take the same file and put it on MDE. I have here a virtual machine with a Windows Defender for Endpoint P2 license. That's for a previous test. Let's delete this and copy the file I created. Let's try it. Click it, and then after a while, Defender for Endpoint will come and complain that Metasploit is being executed. This is from the 26th of August. It's the previous alert. Let's leave it for a minute and I continue because, I'll just continue for now. Let's do it correctly. So basically I need another IP address. So let's change this to the real IP address. This one. Compile it new. It's because it's another VM. The Metasploit server doesn't have the same IP address. Let's take this again. 0.4, copy it. Should start Metasploit. This one didn't work. So let's see if I can delete it, but at least it's not being detected. Cannot. Still running, so it's not being detected. The server is in Germany, so it's a little bit laggy. This is now the compiled file with the correct Metasploit, with the correct Metasploit server, copying it into it. Let's execute it. And we have a Metapreter session, very nice. The problem with this demo is that usually Defender detected Metasploit. This again the old one, but sadly it doesn't anymore, so it's already a bypass, so the last few slides are not that relevant anymore, but if it's not being detected, it's all good. So my idea was basically bypassing file scan is simple, we just use a loader, but then we generate telemetry. But this telemetry is not enough for an EDR to identify a loader or some malicious things. What it really wants to do, most in case of Defender, which I'm focusing on, is a memory scan. It will, upon a trigger, it will scan the memory of a process, of our process, and then find Metasploit. And I don't want this trigger to happen. Usually the EDR, because it needs to be high performance, it needs to select smartly which events it handles on. And, what is dangerous is unbacked memory. So shellcode is usually in unbacked memory. Like here on the right, this is dangerous stuff, there the evil stuff is coming from. So it's usually suspicious. If it's from a baked memory region, it's from the file, and then it's already scanned by the antivirus, so it's not so suspicious. And when does an EDR perform a memory scan? So if you have the typical loader, like on the left, you alloc some memory as read-write, you copy your shellcode in it, you payload, you make it executable, you create a new thread. Usually when you create a new thread, this is a good time for the EDR to scan the memory before you execute it. I don't create a new thread, I just jump to my shellcode. So the second possibility for an EDR to scan memory is usually when you make it executable. So programs execute a lot of virtual allocs, like maybe thousands a second. They copy a lot of memory, which is anyway not visible by the EDR. But making a memory region executable, that would be the perfect time, in my opinion, to scan the memory. So what I do is basically do, I do the same stuff like the loader, just without actual malicious things. So I allocate memory with the same size as my payload, with read and write permissions, copy some fake data in it, change it to executable, and then just do nothing. Just do this 100 times, and then free it again, and then do this whole thing 10 times. This is already also an anti-emulation. It uses a lot of system calls. It uses a lot of instructions, a lot of memory. Probably an antivirus emulator will give up after a few dozen times. If EDR sees a program constantly allocating memory as writable and then making it executable, that's usually an interpreter, Python, Chrome, JavaScript, or anything similar. So in my opinion, sooner or later it will just stop scanning the memory, and that's what we want. So I think everyone knows Pavlov's dogs. If you have a dog breed which drools when they see food, and you ring a bell every time the dog eats, then the dog associates the bell with the food, so you can just ring the bell and the dog will drool from their mouth, even without seeing food. And so in my loader, I just ring the bell a lot. 100,000 times, the dog gets bored and doesn't react anymore. This will be my demo, but I think it still didn't detect anything. That's sad state of EDRs. Okay, no alerts, but we still have our Metasploit. So, conclusion. It will take like 5 more minutes, I think, and then I'm mostly done. The loader, as it is injected into the text section, it's backed memory, so it will not be looked at so much by the EDR, only what the payload is doing afterwards that's more dangerous. But the loading thing is actually not that bad. So basically my bubbles of pain, the file scan is clean, there's nothing to identify. I try to avoid as much telemetry as possible, so the behavior analysis doesn't work. The memory scan I avoided, but some companies, which I also know, do an on-demand memory scan, like once a day or once an hour, where they use PEC for monitor to scan for malicious things. What techniques did I use for my loader, which worked pretty well? Which red teaming techniques invented in the last few years? Nothing. No ETW patch, no user mode hook patch, no memory encryption, no indirect system calls, no call stack spoofing. It's all nice and dandy and looking non-malicious. I took care that I'm not doing some obvious malicious things, threads in unbacked memory, are writable and executable memory at the same calls, APC stuff, and even more, and the rest. What I'm using, of course, is the unbacked executable memory, but this can be fixed too. Noteworthy, of course, is that I used a non-staged Metasploit. So if you have a lot of slashes in your payload in Metasploit, it's a staged version. If you have a lot of underscores in it, it's a stageless version. So you can see my payload is about 200 kilobyte. It's the whole Metasploit. It's not the 10 kilobyte stager. I also disabled autoload standard API. That's a little bit like cheating because the Metasploit will not do much, but still 200 kilobytes in memory. EDR didn't find it. It's not so good. Similarly, reflective DLLs, it can be implemented in an obvious way which an EDR can identify, so I also didn't use this. So I think it's 2 parts. In my opinion, the payload should protect itself. I cannot help it so much. That's also where the experts are, like Brood Rattle or Havoc or whatever. They invest a lot of research to make their payload undetectable. What I want is to load their stuff and to load it without triggering the EDR or antivirus. And I think that's that I achieved. So coming back to the EDR, it has a lot of information, kernel callbacks, ETW, TI, the MC stuff, the user mode hooks, and it gathers even more information. Performance is important, so it doesn't detect much. For the RedTeamers here, if you want to do a loader, I recommend not just using execution guardrails against Middleboxes, which are very powerful. You should do them, you need to do them. Should also add anti-emulation. Yes, anti-emulation, there's a lot of different possibilities. Research a little bit, then do the EDR deconditioning, like I did, which wasn't so necessary, but still good, and see if it's still being detected then. I think these three things are the basics. Make sure you work mostly from backed memory. Don't use writable and executable memory regions. Don't move executable memory regions back to writable. That can be suspicious. Always make sure you have clean call stacks. Try to avoid process injection. If you write a blog article about bypassing EDR, write how, when, with what, how much. Not just EDR bypass, but more like this. I could load a non-staged Metasploit with disabled standard API, also Cohort Strike 4.9, which I didn't show here, and that's the old version, not the cool new 4.10, in Windows Defender on Windows 10 and 11, and Windows 11 with my Defender for Endpoint in August of 2024. So why the title? My first and last shellcode loader. I started doing this shellcode loading stuff this year. Did a little bit of research. So it's my first one. Finally I got around. I'm usually more a Linux guy, but I could use Linux exploitation knowledge for this. And my last shellcode loader, because in my opinion, it cannot be detected really, even though some code can be detected. I can just write some new C code. As a reminder, it's all just C. So it's easy to program. You don't have to use assembly. Can just use virtual alloc like this. It will be resolved by my loader automatically. But there were a lot of bugs. And usually it crashes, and it doesn't say where it crashes. It's just exception, and I have no idea what went wrong. Is it relocations? Did I overwrite the initialization of the process or whatever? But somehow at the end I got it to work. This is just a small summary about a blog article I started. So that's here, blog.deep.ch/post/how EDR works. It has more information, more details, and it's just growing without boundaries. I also written a little bit more about my X-injection, Cordyceps technique, and the SuperMega loader. I open sourced it this morning. Don't know how well it works on other systems, but you can try it. And now I'm more writing my own EDR, a bit of special EDR, to gain more knowledge about all these things. If you want to know more, I can recommend Evading EDR by Matt Hand, the book. It's awesome. I used a lot of tools by Hasharizadeh. She has awesome tools. Check out what she's doing. It's always cool. If you want to know about EDRs, modern, cool EDRs, check Elastic blog. The red backdoor is from mgeeky. Also cool new research. And there was also 2 years ago a pretty good talk about EDR evasion. Not as good as this one, but still. I think I'm already over time. I could continue on until someone stops me. So, for example, we can just preload the DLL, inject it into the text section, and then modify the text section, decode it, and then make it executable again. With this, the payload looks like it's from the backed memory region, which makes the payload less detectable, but I think this modification can be easily identified. Also a cool thing which I liked is the undersized alloc trick. So virtual protect will always work on page level, of course. So we just say we change the protection of 1 byte, then it will change 4,000 bytes. But the EDR will see, I will just scan 1 byte of this memory region and not maybe scan all of our stuff. Also cool is UPX files. UPX has a writable and executable memory. This makes it very easy to just use a shellcode, use Shikata-Ganai, and then inject it there. Should be pretty undetectable. And I think also there's still some things left in developing C2s. I think the loader and the C2 itself can work more together. What Cobalt Strike 4.10 more or less also started with their back-end and caller implementation. So now I'm finished. It's okay. I think we don't have time for questions, but I will be around today and tomorrow. We can always talk red teaming or EDR evasion.
Thank you, Dobin. Let's give him a round of applause, please.
Thank you.